Welcome back to HackCode. In this video, we're tackling an essential problem for coding interviews, longest common subsequence from LeetCode. This problem is great for mastering dynamic programming techniques. We'll explore three approaches: brute force, dynamic programming, top-down, and bottom-up approaches. Let's break down the problem step by step and understand how these solutions work. So sit back, relax, and let's dive in. So let's look into problem statement. Given two strings, text1 and text2, return the length of their longest common subsequence. If there is no common subsequence, return 0. So firstly, if you're not aware, what is subsequence? A subsequence of a string is a new string generated from the original string with some characters, or it can be none, deleted without changing the relative order of the remaining characters. So let me just take an example and explain you. So here we have a string ABCDE. So in this, ACE can be called a subsequence, but it is not a substring. To call it substring, we should not delete any characters. Here ABCDE itself is a substring. It can't be a subsequence. But remember in mind, a substring can be a subsequence, but a subsequence can't be a substring. Okay, so let me take the length 3 here. So for length 3, if we skip B, it is called a subsequence. Okay, the relative order is remained same. Okay, and then here this is not a substring. So here ABC is a substring. So you got the difference, right? Substring, we can't delete any characters. Okay, in subsequence we can delete the characters, but a substring can be called a subsequence. Okay, and then next what they said, a common subsequence of two strings is a subsequence that is common to both strings. So basically the subsequence should be common to the both strings. For that subsequence only we have to consider the length and return the longest common subsequence length. That is the question, guys. So let's look into example. So in example 1, we have text1 as ABCDE and text2 as ACE. So here, what is the common subsequence? You know that ACE can be a subsequence of this string. So here this is one subsequence, and then in this string we can find ACE, right? ACE. So now what is the longest common subsequence? It is 3. So that's why we output 3. Okay. In example 2, we have ABC. So these two strings are same, and I already told you that a string can be subsequence of itself. So the output is 3 because the length of the string is 3. In example 3, text1 is equals to ABC, text2 is equals to DEF. So we see that there is no common character between these two strings. So there is no common subsequence. So that's why we output 0. Okay. What are the constraints given? Text1 and text2 lengths are in the integer range of 1 to 1000. That means that whatever strings they give are in the integer range of 1 to 1000. Okay. From this, what can we think of? So basically here we can consider solving this in O of n square. Okay. So O of n square, or it can be O of m into n, because the strings are of not same length. So that's why we can say it O of mn. Okay. So if we consider it O of mn, so in the worst case, what it would be 10 power 3 into 10 power 3. It is 10 power 6. But we can perform 10 power 8 operations per second, right? So if we solve this in O of n square complexity, then that is good. Okay. So I told O of n square by assuming this two strings have same length. Okay. In that case only it's O of n square. But actual problem they give us a different length, m and n. Okay, it's not the same length they mentioned. Okay, so we can consider O of m and complexity. Okay, and in constraint 2 we have text1 and text2 consist of lowercase English characters only. So they mentioned that what is the characters we have for text1 and text2. Okay, so this is the boilerplate code given we have, wherein we have a longest common subsequence as a method, and then this takes text1 and text2 strings. Okay, and then it returns integer. So basically this integer is what? The length of the longest common subsequence. Okay, you got the idea, right? Now let's look into the approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So let's look into brute force approach. What is the intuition here? For each character, we have two choices. Include it in subsequence if it matches, or skip it and try the next character. So basically, if you don't get it, so we have these two strings, right? So for these two strings, if these two characters matches, then we can include in our LCS, or as longest common subsequence. Okay, and then we can try checking for the other characters. This was the idea. So in the case where this character doesn't match, like if we consider B and C, so here what we can do, we can either exclude B or we can exclude C. Okay, so if we exclude B, we can compare C with C, and then if we exclude C here, we can compare B with E. So that's the idea, guys, here. So basically we'll repeat this process recursively, and this would result in all possible subsequence combinations between two strings. Okay, so although this approach seems effective, this won't scale for larger inputs due to the redundant computations. So don't worry about this part, we'll look into this further. Okay, so firstly let's explore the approach we just discussed. Okay, so here what we have, we just discussed that we have a recursive call. So firstly we start our comparison from 0th index. So here for 0th index we have AA matching. So we proceed with further comparisons, that is in the next index 1 1. So we compare B with C. So here B and C are not matching. Now guess what we discussed, right? We can include B in our comparison and exclude C. In that case we can check for the indices 1 from this string and 2 from this string. So that is we are comparing B and D, or else we can exclude B and compare C with C. Okay, this is what the possibilities we have. So we are passing 2 comma 1. So basically these two indices we are passing, this is a recursive call. So this is index of this string and this is the index of this string. So 1 is what here C. Okay, so for this thing we are comparing C with C. So C and C matches, right? So in this case we can just simply proceed with a further comparison, that is comparing D with E. So we are passing 3 and 2 to this recursive function. So for that reason we can exclude D and compare E and E, else like we can include D. So if we exclude D, what is the indexes we have to pass? We have to pass 4 and 2, because we just need to skip this and send the 4 comma 2. So if we include D, we have to pass this 3, and then we have to pass the next index from this string, which is 3. But 3 is not valid index in this string, right? So here only till 2 it's valid. So if it reaches 3, then we can stop the call. That's the idea. So after this, in 4 and 2 here, so we have 4 and 2. So E is matching with E. So in this case we can increment the indexes for comparison. So 5 and 3 would be invalid indexes, right? So that's why we stop the comparison here. So coming back to this call 1 comma 2. So here we are comparing B with E. So in this case B is not equal to E. So what we do, we just exclude B and check with C and E, or else we include B and pass the further index here. So if we exclude B, we have 2 comma 2 indices here, 2 from here, 2 from here. Okay, so here C is not equal to E, and the same case repeats. So for this we exclude C, so and we get 3 from here and 2 from here. So we pass 3 comma 2. In the other case we can include our C and then exclude the E here. So in this case we get 2 and then we increment the index here, right? So that's why we get 3. So but this is not a valid index, that's why we just stop the call here. Okay, you got the idea, right? So basically we repeat this approach recursively. That's the main intention, guys. So if a character matches, we just go with the further comparisons. If a character doesn't match, we just go with the possible combinations, that is like excluding one character and comparing from one string. So we try both ways. So we exclude one character from each string and then we try comparing with others. Okay, so now let's look at algorithm. So as we discussed, we define a recursive function that takes the two indices I and j representing the current index position in text 1 and text 2. In step 2, if characters at text 1 of I and text 2 of j are matched, we move to the next character in both strings and add 1 to the LCS count. Why we add 1? Because we consider this character to our LCS, right? So that's why we add 1 to the LCS count and we proceed with the further computations. So in step 3, if the character doesn't match, we recursively explore both possibilities, like moving to the next character in text 1 or text 2, and we take the maximum LCS length, because the question asks us to return the length of the longest common subsequence. That is, we have to return the maximum possible longest common subsequence length. That's what we're doing here. So that's why we have to take the maximum. In step 4, we continue until one of the strings is fully traversed, then return the accumulated LCS length. Simple, right? So it's just a basic thing we just discussed, so nothing complicated. Let's look into code here. So firstly, here we define our recursive helper function, which takes the two indices I and j. So for this recursion function, there should be a base case, right? Else the recursion would go on happening. That would give us the maximum depth exceeded error. Okay, we should have some stop condition for recursion. Okay, else it keeps on calling itself infinite times. Okay, so here the base case is when one of the string is completely traversed, we don't need to continue further, right? Because there would not be any common subsequence, right? The common subsequence exists only if there are two strings, right? If one of the strings is exhausted, then that means that we don't have any commonality. That's why we have to return 0. So here that case we can get from comparing with index with the length of the particular string. So if I is equals to length of text 1, it means that all the valid indexes for text 1 is exhausted. We know that the valid index for text 1 only till 0 to length of text 1 minus 1, right? So that's why if I reaches the length of text 1, then it means that we can return, or also if j reaches the length of text 2, we can return 0. Okay, so we proceed to step 2 only if this is not the case. So in step 2, if characters match, we move to the next character in both strings. Okay, so that's why we're just checking if text1 of I is equals to text2 of j. In this case, then we can just continue with the further computations. So we consider passing I plus 1 or j plus 1 because we consider the I here in this recursion and we passing I plus 1 and j plus 1 in the next recursion. So we have added 1 because currently both characters are matching. So this can extend our LCS. That means that they can form our LCS, right? So that's why we add 1 plus and we call our function here. Okay. In step 3, this is the case where our characters don't match. Then we have to explore the both possible moves. So for that, we can either include I or we can include j. So if we include I, we have to pass I plus 1. This is saying that we consider I in this recursion, and in next recursion, we are considering I plus 1. And also here we are passing j as is. That means that j is not processed in this recursion. So here only I is considered. So in another call, we are making with I and j plus 1. This means that you guessed it right. We consider j in this recursion, and for the next recursion, we are considering j plus 1. Also here we are passing I as is. So that means only j is considered. Okay. So we consider either one of this. This is our possibilities. We just saw in the recursion stack here we discussed, right? And we are returning the maximum out of these two values because we want the maximum longest subsequence time. That's why we take the max out of these two values. Okay. And this is our recursive helper function. So simply here we are calling our recursive helper function by passing 0, 0. This is the index we have. Okay. So what are the complexities here? Time complexity is O of 2 power m plus n, where m and n are lengths of text1 and text2 due to the exponential growth from recursive calls. So why it is exponential? So if we consider a simple case, if you have a string of length m plus n, and for each character we have two possibilities, either to include or exclude. So these two possibilities we have to multiply till what? M plus n times. So it is 2 power m plus n. Okay. That's why the time complexity is O of 2 power m plus n. And the space complexity is O of m plus n due to the recursive call stack. We know that, right? The recursive call stack would be of depth of m plus n. That's why the space complexity remains O of m plus n. Basically, we have to process these two strings, right? That's why. Okay. I got the code ready here. Let me try running this. So the solution is accepted for these three cases. Let me try submitting this. So we see that time limit is exceeded, guys. So basically this is the exponential time complexity and won't be scalable for the larger input. So only 17 out of 47 test cases are passed. Okay, so that's why we have to consider optimizing this. Okay, let's discuss the optimized approaches. So let's look into the recursion stack again, but with a closer look. So firstly here, if you see, we are recomputing our subproblems. So here 3,2 is subproblem, right? So this is computed for twice in this call and in this call. And then we have 4,2. This is also repeated for twice. And 3,3 also repeated for twice. So even for a smaller length strings, we are recomputing this again and again. Like we can see that this many recomputation of the subproblems. So what if the string length is large? Then it would become more number of recomputations, right? That means that we are computing again and again. So that's what I mentioned here, redundant computations. So if we compute this once and store the result, then we can reuse it again, right? That's the idea, guys. So basically what I'm talking is the dynamic programming top-down approach. So now let's explore that approach. Basically it's the same recursion but with a memoization. So basically we store our results once we compute it, and next time we don't compute it again, we just send from the result storage. Okay. So what is the intuition here? This approach builds on the recursive solution but improves the efficiency by storing already computed results in a cache. So here some cache, we call it as a dictionary or hash map. Okay. In Python it is dictionary. In general it is a hash map concept. In hash map we store our computed results. Okay, this is a memoization approach because we're storing our earlier computed results. That means that we are storing it around memory. That's why it's a memoization approach. Instead of recalculating the LCS for every IJ pair, we store the results in a dictionary to prevent redundant calculations, significantly speeding up the process. So basically, if you don't recompute this again, that means that it is speeding up our process, right? That will help us in optimization, guys. So let's look into the algorithm. Firstly, we define a recursive function that takes two indices I and j. This is same as previous thing. And here, this is what difference. We use a dictionary memo to store results of each ij combination. If text of I and text of j match, increment the LCS count and store the result in the memo. Okay, so before we returning the result, we storing our memo. Okay, and in step 4, if characters don't match, take the maximum LCS length between the two recursive calls, storing the results in the memo. So basically the idea here is, firstly we have to check in cache before computation. Okay, So if it is already computed, then we can just return the result. If it is not computed, we compute it and store our cache and then we return the result. That is the idea. So let's look into code. You'll get a more idea. So here we have the same function but with a different name. Okay, so this is our previous approach code, this is a current approach code. Here we named it LCS memo because we are using the memo dictionary here. Okay, so here firstly this is the same base case. We're checking if index is reached the length, then we return 0. And the next step what we have, we are checking if I and j combination exists in our memo. So memo is our dictionary here. Okay, so firstly we are checking our dictionary before even computing. That's the difference here, guys. And then this step remains same, right? See, so here we just calling LCS memo by passing the same indices as we pass here. And in step 4 as well, we check the same thing, but we store this in our memo before returning. Okay, so we store in our memo here and we return here. Okay, so basically here we're storing it as a tuple. Okay, this hash map should contain only immutable keys, so we can't store it as a list. List is mutable, so tuple is immutable. That's why we store it as a tuple. The tuple is ij here. Okay, if this is already computed, the value would be there in our memo. Okay, we discussed, we firstly check in memo. If it is already computed, we just return it, and then if it is not computed, we compute it and store in our memo and then we return it. That's the idea, guys. Same code. Okay, we just use the memo here. So order complexity here, the time complexity is O of m into n, where m and n are lengths of text 1 and text 2 as each subproblem is computed once. So basically for text 1 we have m subproblems and for text 2 we have n subproblems. So on total we have m into n subproblems. So that's why the time complexity is O of m into n. The space complexity is also O of mn because for memo dictionary we store each ij state, right? So we have such m into n states. That's why the space complexity is O of m into n. I got the code ready here. Let me try running this. So this is the accept solution for 3 cases. Let me try submitting this. So this is accept solution for all the test cases we have. So let's look into our bottom-up dynamic programming approach. So here in this approach we use a DP table where DP of ij represents this LCS length for the substrings text 1 and text 2. So here this represents the length, right? So that's why we consider this slicing here. For slicing, this index is exclusive range. So text 1 would be considered only till 0 to I minus 1 and text 2 will be considered only till j minus 1. So that's the idea, guys. Basically this has to represent the length, so we're translating that length to indices. Okay, that's why we're using the slicing here. This is how the DP table looks like when it is completely filled, but don't worry, I'll show you how to fill this from scratch. So here we have a DP table and we'll fill it together. Okay, so here we start from the first character and we iterate to each possible pair of indices. So this is same as previous approach where we did recursion, but here we're doing the iteration, that's all. So this also we discussed in previous approach, right? If character match, we extend the previous LCS length by 1. Otherwise, we take the maximum LCS length from either excluding the current character in text 1 or text 2. Okay, this is the same as previous one. So here in this DP array, so we represent this first row and first column to be 0, 0 to represent the states where either of the strings is empty. So here the first row correspond to the case where text 2 is empty. That means that this text is empty. So it is not empty right now, but consider when it is empty, this should be all 0 set because there can't be any common sequence. When this text 2 is not at all there, we don't have any common subsequence. So this state of DP array represents that particular combination. Okay, and this column represent when text 1 is empty. So all entries would be 0. Basically here we can't be having any common subsequence, right? So that's why we have to represent that using the zeros here. Okay, so remaining DP of ij represents the length of the LCS of prefixes of text 1 and text 2. So for example, we consider DP of 2, 1. So as we discussed initially, we do the slicing. So after doing slicing, what we get? So text 1 of 0 to 2 we do, right? So it gives us AB because C is exclusive. This is slicing range, this is exclusive. Okay, and then we also slice till j for second string, which is text 2. So if j is 1 here, we slice from 0 to 1, which gives us only A. So here DP of 2, 1 represents the longest possible LCS for A, B and A strings. So here DP of 2, 1 is what? 1. So basically this is the longest possible common sequence for these two substrings. Okay, so now let's look into filling this DP array. This is very interesting. I'm sure you definitely like this. So firstly, we fill this first row and first column to be 0 to represent LCS when one of the string is empty. So this is the case when this string is empty and this is the case when this string is empty. Okay, and then now we start filling the other cells. So firstly, we try comparing A and A. So A and A are matching. That means that we can consider our LCS. So we can put 1 here. So after that, we consider comparing A and AC. So here A and C are not matching. It means that we can exclude the A here and we can consider the LCS only with AC. So when A is not there, what is the LCS possible with only AC? It is 0, right? It is mentioned here. So this is one case. So if we exclude C, what is LCS possible between A and A? It is 1. So max of these two is what? 1. So it is 1. This case also A and E are not matching. So that's why we exclude this one and get the LCS. So what is LCS between A and AC? That is 1. This is one case, and then we exclude A. So what is LCS possible only with ACE? It is 0. So basically we are comparing these two cells, right? And then we're bringing the max out of it. So here max is 1. That's why we filled it 1. So you got the formula, right? So basically when current characters doesn't match, we just take the max out of these two cells and fill the DP area at that particular index. Okay. So now we're done with this row. Now let's go to this row. We have string A, B and A. So here B is not equals to A. That means that we can exclude either B or we can exclude A. So when we exclude A, what is the length of LCS possible? 0. That's what we have here. And then when we exclude B, what is the LCS possible? We have AA is 1. So this is 1 because this is max of these two and this is 1. This is a case of filling AB and AC. So now we compare AB with AC. So here what is it? B is not equal to C. So similarly, we have to get the max out of these two values. That is 1 here. So now we have to compare AB with our ACE. So here also we don't have these two characters matching. So you got the idea, right? So basically we have to take the max out of these two and fill here. So that's why we filling 1. So now we have to compare ABC with A. So here also these two characters don't match. So we get the max out of these two and fill this. So that's why here we fill 1. So next is we compare ABC with AC. So here we have these two characters matching. This is where it becomes interesting, guys. So here since these two are matching, we consider this LCS as length 1 and then we have to go back to our previous subproblem. One level below we have to consider, right? That is AB and A. So basically these two are matching. Then we have to consider the subproblem, right? And the subproblem is AB and A here. So for AB and A, what is LCS possible? This one. So when these two are matching, the formula is we fill 1 plus and this cell's value, which is 1. So this becomes 2. Okay. So now ABC with AC. These two don't match. That means that we have to take the max out of these two and fill this. So it is 2. So now we have to compare ABCD with A. So here these two don't match. That means we have to get the max out of these two and fill this. That is 1, guys. So now D with C. So these two don't match. That means that we have to fill this with the max of these two. So which is 2 here, right? That's why we fill 2. Next we have D with E. So these two don't match. We have to fill with max of these two. So that's why we fill our 2. So now we compare ABCDE with A. So these two don't match. So that's why we fill it with the max of these two, which is 1. So next is we compare this with this and these two don't match. So that's why we take the max of these two and fill this, which is 2. So next we compare E with E. So here E is matching with E, right? So next what we have to look? We have to look for the subproblem. So which is this one and this one. So for these two strings, what is the LCS? We have it stored here, right? So basically we had to account for the current character and the previous subproblem, which is 1 plus 2. This is 2, right? That's why it's 1 plus 2. So now the total is what? 3. So we fill with 3. Now this cell contains what? LCS of these two strings. So for these two strings, we can just directly look up this cell and return the answer, right? Which is dp of m comma n. So if we see this, we have this cell as 3 and the answer is also 3 here. So you got the idea, right? Basically, we have to look for this cell after filling the dp table and return it, okay? So now let's look into our algorithm. Algorithm is nothing but what we discussed just in form of steps. So first we initialize a 2D DP array with dimensions of length of text 1 plus 1 and length of text 2 plus 1. So basically it is m plus 1 and n plus 1 dimensions, okay, to show the LCS values, okay. And step 2, iterate through each character pair in text 1 and text 2 using the nested loops. So basically here we need to iterate the two strings, right? That's why we have to use the nested loops. And in step 3, if the characters at the text 1 I minus 1 and text 2 j minus 1 match, set dp of ij is equals to dp of I minus 1 j minus 1 plus 1. This is something we just discussed, right? So here if these two characters are matching, what we just did, we just consider 1 plus and this character. So if we consider this cell as ij, so what are we going for? We're going for I minus 1 and j minus 1. So basically here I is the row and j is the column, okay. So here we're going back from row and column and fetching this value and we're just adding 1 to that. That's what we're doing here when two characters matching. So you got this. And in step 4, if they don't match, set dp of ij to the maximum of dp of I minus 1j and ij minus 1. So it is nothing complex, guys. We just did here, right? So when these two don't match, what we did, we just took the max out of these two values. So here, how can we get this value? If we consider this as ij, we are just going to the previous column, which is j minus 1. So this is ij minus 1, and this is what? This is I minus 1 j. So for this cell, what are we taking? We are just considering the previous column, that is I and j minus 1, and this how are we getting? So basically this is what the previous row, I minus 1, and the same column, so it is j. So we taking the max out of these two. So that's how we got this formula. It's nothing complex, okay? So let's look into the code. So firstly, here we're getting the length of text1 and text2 and storing into the m and n variables. Basically, we need this for our iteration purpose. And then what we are doing, we initialize a DP array with dimensions based on the input strings. So here we initialize the DP array of dimensions m plus 1 cross n plus 1. So this is the list combination way of doing it. So before that, I'll just give you a basics, okay? So if we consider this 2D array, so let's say we have 1 2 1 and 2 1 2. Okay, so if you represent this in this format, 1 2 1 2 1 2. So here, what does this translate to? This translates to number of columns, right? And then this length of this external list translates to number of rows. Okay, so basically what we are doing here, inside the list we are forming the columns, right? So here this is from the columns 0 into n plus 1. You know, right? 0 into n plus 1 will give what? 0 0 0 0 till n plus 1 times. And then this is repeated for what? M plus 1 times. So this is forming that many rows. So basically, you know, right, like length of this external list is the rows, and then we are repeating this for how many times? M plus 1. So we have m plus 1 rows and n plus 1 columns. That's the idea, guys. Very simple. Okay, in step 2, we iterate over each character in text1 and text2. Here we starting I from 1 to m plus 1. So here m plus 1 would be exclusive. The inclusive range is 1 to m. We already filled the 0th row and 0th column, right? So this is to represent when this string is empty, and this is to represent when this string is empty. Okay, so we have to go from first index. Okay, in step 3, if characters match, take LCS from previous diagonal cell plus 1. So here, how can we refer to the character? Basically, this is a length, and then we have to convert this into character. That means that we have to do minus 1. So text1 of I minus 1 is equals to text2 of j minus 1. So basically, we are converting this length to our index. Okay. So in this case, we're filling this DP array ij, which represents the LCS length, by DP of I minus 1, j minus 1 plus 1. This is what something we discussed here, right? So in other case, where these two characters don't match, we have to get the max out of these two values. This is the same thing we just discussed here, okay? So at the end, after completing all the iterations, we return the DP of mn, because we know that LCS of these two strings would be stored at this cell. So that's why we return DP of m and n, okay? So what are complexes here? The time complex is O of m into n, where m and n is the length of the text1 and text2. Basically here we're iterating the loop for m times, and here also n times, that is m cross n. So that's why it's O of mn. And the space complex is O of mn for the 2D table DP, okay? So basically here we are storing till m plus 1 and n plus 1, right? This one and this one are negligible in front of m and n. So that's why it is O of mn, okay? I got the code ready. Let me try running this. So this is the accept solution for 3 cases. Let me try submitting this. So this solution is accepted for all the test cases, and it almost meets 84% of the users. So congrats, guys. Just learned 3 different approaches. One is brute force, next is dynamic programming top down, another one is dynamic programming bottom up. And that's a wrap on solving the longest common subsequence in 3 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.